Hi, this is Dane Quinn from the University of Akron, and today I'd like to record a video lecture on vectors. So why do we even want to think about vectors? Well, it's because the elements of dynamics, things like position and acceleration, forces, moments, they're all naturally described by vectors. As a result, the laws of mechanics and the way that we describe the world is based on vectors. So what's a vector? Well, it's a mathematical quantity that describes multiple independent variables. We typically think about vectors having magnitude and direction. And of course, they obey laws of vector addition and scalar multiplication, as well as operations like dot and cross products. You've probably seen vectors before in the past, but I really want to go through and talk about them in the context of kinematics. Right? So we think about vectors as geometric objects, right? So in particular, we think about vectors as arrows, right? So they are represented geometrically. And we said above that they have typically magnitude and direction. So again, they're represented geometrically with an arrow. And we'll define this arrow as, say, R with an underbar. So this is important. In terms of notation, and we'll use notation a lot in this class, vectors have underbars. Like R underbar. Unless, and this is the notation we'll use in class, unit vectors. So unit vectors have length 1 by definition, and those get an overhat. Also a little cap on the top. So if you see an underbar, that's a vector. And it could have unknown direction, unknown magnitude, or it could have known either one of those. But if you see a hat over the top, that is specifically a unit vector, right? So that is something that has, by definition, length 1. The other important thing is that the vectors are defined independently of how we choose to measure them. Right, so again, you can think about this as an arrow. And this arrow is the arrow, regardless of whether we measure the length of the arrow and the orientation, or say components in different directions, right? It's still the same arrow. Right, so again, these vectors are geometric objects. They are independent of how we choose to measure them, and we'll talk a little bit about coordinates and such. And again, notation-wise, we always define vectors with underbars. Now, I realize that you may have had other classes where they might define them with the bar on top, right? Or in a textbook, you may see them as boldface, right? But here in this class and in the notes that I will develop, I will be consistent. I will always use this underbar to denote a vector, unless it has unit length, in which case it gets a little hat. Right. So, again, we've said that the vectors are defined by magnitude and direction, and the magnitude represents the length of this vector, and the direction represents, well, the orientation with respect to some predetermined set of bases. So what's a basis? Well, it's an orthogonal set of unit vectors. So here I've drawn two sets of bases, right? I and j, and notice that these are hatted, right? So they have little hats on the top. So they are, by definition, unit vectors, indicating really only direction, right? So I and j are horizontal and vertical, right? Of course, if you stand your computer screen up. E1 and E2 are some other set of directions, right? So if I look at I and j, I will assume that these are reference directions. And in particular, they are fixed in space, or in this context, fixed in the plane of the computer screen, right? So they are unchanging. I and j are always in the directions shown. If you notice, I have another set of directions, E1 and E2. And looking carefully, E1 is in the same direction as this vector r, right? So here, E1 and E2 are referred to as moving directions, right? So as r changes its orientation, as r moves around, then E1 and E2 could move around as well. So which set of directions we choose to use really will affect the coordinates that we use to measure this vector. Right, so what are coordinates? Coordinates are measurable quantities that specify the vector. So, again, in terms of these directions, we have two common sets of coordinates. The first we'll look at is Cartesian coordinates. So, we'll define the vector r in terms of components in these reference directions, right? So I and j. So doing that, basically we will define x as the component of r in the I direction, and then we'll define y as the component of r in the j direction. So given the coordinates x and y, we can describe the vector r. Now, the other way that we can do this is with polar coordinates. So with polar coordinates, we will explicitly define magnitude and direction. So here, r will be r, the magnitude, right? So that's going to be the length of this vector in the E1 direction. Now, to define the E1 direction, we need a second coordinate, which we'll use as theta, right? So here, r is the magnitude, and theta defines the direction of E1. Right, so our coordinates here are r, and notice that this is a scalar. It doesn't have an underbar, even though we use r in two different places. One of these is a vector, and one of these is a scalar. I kind of did this on purpose, just again to emphasize that our notation allows us to distinguish between vectors and scalars. And then the second coordinate is theta. When we use Cartesian coordinates, we also need two, and those are given by x and y. So now we said that this vector is independent of how we choose to measure it, right? So xi plus yj is equal to r. But that's also equal to r in the E1 direction. So regardless of how we choose to measure the vector, right, it is the same geometric quantity, just here in terms of two different representations. So again, I've kind of listed all of that again, right? So we have I and j, E1 and E2. Here are our two different representations for the vector r, right? And over here we again have a picture of how x and y and r and theta are all defined. And so now, given this, we can relate directions. So in particular, we can describe E1 in terms of I and j. And actually, we'll also describe I and j in terms of E1 and E2. So let's look at this one first. Right? So this is the one that's probably going to be the most straightforward. So if I think about E1, right, how do I define E1 in terms of I and j? Well, I'm going to draw this little triangle, and this is a right triangle. Right? So this side is the hypotenuse, and it has unit length. And then with some trigonometry, the adjacent side is cosine of theta, and the opposite side is sine of theta. Right? So looking at this triangle, right, these are the sides for unit length, hypotenuse. So now, if I were to describe this vector E1, it's cosine of theta in the I direction plus sine of theta in the j direction. So now if I want to describe E2, I'll do the same thing. I'll define this triangle. Again, here's the angle theta. And so we see that E2 is equal to minus sine of theta, because I have to go in the minus I direction, plus cosine of theta in the j direction. So here we've defined E1 and E2 in terms of I and j. We can also do the same thing except for I and j in terms of E1 and E2. So notice that these two pictures are exactly the same. I've just kind of taken this one and I've rotated it so that E1 and E2 look horizontal and vertical. But now we'll do the same thing, right? So if I want to describe I need to find the length of the projection onto the E1 vector and onto the E2, right? So here we have, again, this right triangle. This distance is cosine of theta. This distance is sine of theta, right? So we see that I is equal to cosine of theta in the E1 direction, but now minus sine of theta, because we're going down, in the E2 direction. Likewise, j here is equal to sine of theta in the E1 direction plus cosine of theta in the E2 direction. So now with these, we can actually use these relationships to help us relate the different coordinates that we've measured here. So notice that r, or recall that r again was x in the I direction plus y in the j direction, which is r in the E1 direction. Right, so I'll just recopy that. But r is equal to the vector r in the E1 direction, where E1 is cosine of theta I plus sine of theta j. So just comparing this and this, we see that in the I direction, we have x is equal to r cosine of theta. And then looking at the j direction, we see that y is r sine of theta. Now, you knew all this stuff, right? This is just trig. But we can develop a lot of these relationships, and we can use this in the context of these vectors and these basis directions. So now we'll turn to some of the operations that we can use with vectors. So here I have three vectors, A, B, and C. And what we see is that C is equal to A plus B, right? And this is vector addition. We said before that vectors can be defined independently of any specific set of coordinates and directions. But let's go ahead and represent these in terms of I and J, right, which are our fixed reference directions in the ground. So as a result, we see that the vector A can be xa in the I direction plus ya in the j direction. So here this would be, say, xa, and that length would be ya. Likewise, B is xb and yb. Right, so this would be xb, yb. Note here that for this picture, yb would actually be negative, right, because this describes the displacement of the vector in the plus j direction, and here this one's going down. And then finally, C is defined in terms of these two components. So xc in the I direction and yc in the j direction. So as a result, because of this vector addition property, xc in the I direction plus yc in the j direction is xa I y a in the j direction plus xb in the I direction and yb in the j direction. So we can relate these. The I component reduces to xc is equal to xa plus xb, and yc is equal to ya plus yb. So this is an example of vector addition. Well, we also have scalar multiplication. So given a vector d, right, and so let's let d, again in terms of I and j, be equal to xd in the I direction plus yd in the j direction. Then if I multiply that by 2, right, so twice d is going to be, essentially this vector. Let's do that in red. Well, that's just going to be 2xd in the I direction, 2 times yd in the j direction. Right, so basically the components are in the I and j directions are doubled. Right, so the blue was the original and red is the scaled values. Likewise, I can also multiply this by, say, minus 1. Right, so minus d would be minus xd I and minus yd in the j direction. Right, so here this vector would be drawn like so. And then here would be the components in the, again, I and j directions. So here scalar multiplication leaves the direction unchanged. And in terms of coordinates written based on the reference directions, these scalar multipliers just move through into each component. So the next thing that we'll be interested in is a dot product. So the dot product operates on two vectors and then gives a scalar. All right, so we'll take two vectors and from that produce a scalar quantity. So this is defined really based on what happens with perpendicular and parallel vectors. Right? So if I have I and j, and I take I dot I, and again these are unit vectors, right? So that they all have unit magnitude. That's defined as 1, right? And likewise j dot j is equal to 1, and then I dot j. So perpendicular vectors have a 0 dot product, and j dot I is equal to 0. So this is really enough to completely define the dot product between vectors. Right? So if I think about two vectors here, a and b, and a would be xa in the I direction plus ya in the j direction, and then b would be xb in the I direction plus yb in the j direction. Then a dot b is equal to, well, let's go ahead and work all this out. xa in the I direction, ya in the j direction, dotted with xb in the I direction and yb in the j direction. Right, so we'll just carry all this stuff through. And I will do this one time. I'll probably never do it again in this class. Right, but we end up with xa, xb, I dot I, so that's these two terms, plus xa, yb, I dot j, plus ya, xb, j dot I, and finally ya, yb, j dot j. And again here these components xa and xb, for example, are basically the components in the I and j directions. So this ultimately equals xa, xb plus ya, yb. So this is the dot product between two arbitrary vectors. And notice that this is also equal to b dot a. So now, if I look at this picture, here we again have this vector a, and I've defined two new directions, I2 and J2. So if we have a unit vector, just in general we'll call it E, and you can tell it's a unit vector because it has this hat over the top, then A dot E is the projection of A onto E. Right, so here, if E is, we're going to use I2, then the projection of A down onto the I2 direction is this length. Right? So this length would be A dot I2. And likewise, if I were to project onto J2, I would get that length. So that's going to be useful for us as we go forward. And then finally, we can calculate the magnitude of a vector by using the dot product. So here, the magnitude is represented with these two vertical lines, kind of like an absolute value. And it's actually defined as the square root of A dot A. And what we see is that becomes, in terms of these coordinates, xa squared plus ya squared. Imagine you went back up here and A and B were the same thing. Then A dot A would be x squared plus y squared. And then again, the magnitude is basically the square root of that. So this idea of taking the dot product of something with itself will be useful for us when we need to find the magnitude of a vector. So finally, our last operation is the cross product. So the cross product works on two vectors and produces a third vector that's perpendicular to the original two. Right, so here I've drawn I and J, and then K comes, essentially this is now a three-dimensional picture, so it comes out of the plane of I and J. So now the cross product is defined with really these 9 rules. Right, so if I take a cross product of anything with itself, I get 0. So I cross I is equal to 0, J cross J is equal to 0, and K cross K is equal to 0. When I take the cross product of two different perpendicular vectors, those follow the right-hand rule. So I cross J, and I would put my hand out at the end of I, curl my fingers around towards J, and then my thumb of my right hand points in the K direction. So if I look at J cross K, for example, where's that one? Over here, I get I. And then finally, K cross I is equal to J. And then the final 3 are given as shown. So J cross I is equal to minus K, K cross J is minus I, and I cross K is minus J. So the way that I remember this is I will just write these out. I, J, K in order, and then once I get to K, I'll start over again and write I and J again. If I cross going to the right, it's positive, and if I cross going to the left, it's negative. So I cross J is equal to K, J cross K is equal to I, K cross I is equal to J, and then if I cross going to the left, I get a negative sign. I've also seen this with triangles and circles and clockwise and counterclockwise. However you want to remember the cross product, fine by me. Right? Just remember it somehow. So in general here, let's go back and look. Right? If I have A is XA in the I direction plus YA in the J direction, and B is equal to XB in the I direction plus YB in the J direction. Notice that these two vectors exist in the plane of I and J, and we're dealing with planar kinematics here in this course. So all of our starting vectors will be in this sort of I, J plane, and then K will come out of the board if we were actually in a lecture hall, or out of the computer screen if you're watching this online. So then A cross B is equal to XA in the I direction plus YA in the j direction cross XB in the I direction and YB in the j direction. So notice that this is going to simplify considerably, and I'm not going to write all these out. I'm just going to write out the ones that are non-zero, right? But we essentially take these and distribute them through, right? So we get I cross I. Well, I cross I was equal to 0. So the only one that's left is XA YB times I cross J, and then YA XB J cross I, because J cross J is equal to 0. So now, going back up and comparing this to what we have before, or using the right-hand rule, or this device, we end up with XA YB minus XB YA, all in the k direction. So this vector becomes A cross B. Notice that if I had B cross A and I worked all of this out, I would just get the negative of A cross B. So this is unlike the dot product. Dot product, I can switch the order here and I get the same thing. With the cross product, if I switch the order, I get the negative of what I had before. Right? So B cross A would actually be down in this picture. Okay, so finally, a little bit of use for this. This is not a trig class, but there will be a lot of trigonometry in this. So let's go through and look at some various scenarios. And really what I want to do here is calculate I2 dot I3. So I want to calculate the dot product between these two vectors. How am I going to do that? Well, I need to know the orientation of each of these vectors, right? So we'll go ahead and define I and j as reference directions, and then we'll let theta 2 be the orientation of I2 with respect to I and j, and then we'll let theta 3 be the orientation of I3 and j3 with respect to I and j. So now, looking at this, right, going back to our relationship between directions, we see that I2 is cosine of theta 2 in the I direction plus sine of theta 2 in the j direction. J2 is minus sine of theta 2 in the I direction plus cosine of theta 2 in the j direction. Likewise, I3, J3, I3 is cosine of theta 3 in the I direction and sine of theta 3 in the j direction. Notice that these two look almost identical, except here we've used the angle theta 2 and here we've used the angle theta 3. Right? But in terms of that angle, they actually have exactly the same representation. So J3 is minus sine of theta 3 in the I direction plus cosine of theta 3 in the j direction. So here we have written our directions I2 and I3 in particular in terms of I and j. So we could take a dot product. Well, actually, if I just go back and look at this picture again, the angle between these is theta 3 minus theta 2. So if I wanted to find I2 dot I3, right, I could go through and draw my little triangle, right, or look at the projection of I3 onto I2. So when I do that, we find that I2 dot I3, just looking here, is cosine of theta 3 minus theta 2. And Doing that again in terms of I and j, well, I2 was cosine of theta 2 in the I direction plus sine of theta 2 in the j direction. I3 is cosine of theta 3 in the I direction and sine of theta 3 in the j direction. Well, working through these dot products, I get cosine of theta 2, cosine of theta 3, and then sine of theta 2, sine of theta 3, because the I dot j terms are 0. It's only the I dot I and j dot j terms that remain. So now we can compare. Right? This was I2 dot I3 when I calculated the dot product directly. And this was I2 dot I3 when I calculated the dot product in terms of I and j. Well, these two things have to be the same. So ultimately what we have is that cosine of theta 3 minus theta 2 is equal to cosine of theta 2 cosine of theta 3 plus sine of theta 2 sine of theta 3. You may recognize this. This is one of these sort of angle addition trig formulas that, maybe you learned in 11th grade. There's a bunch of these. And in fact, all of them can be properly derived in exactly the same way, just depending on how you define your directions and what dot products you take. So for example, if I were to take a dot product between, say, I2 and J3, I might come up with an appropriate relationship between sine of combinations of angles. Right? So this idea of using different directions is actually very powerful, and one that we'll make use of a lot during this course. So the reason that I really went and spent a lot of time in this lecture is because we need a really good foundation of vector algebra in order to do some of the kinematics that we'll need to do coming up. So that's it for today. Thanks a lot. This has been a pretty long lecture, probably the longest one that I will record all year. But it is a background. It is background work and hopefully a review of things that you have already seen before. So that's it. Thanks a lot, and I will talk to you again. Take care. So if you look carefully, E1 is in the same direction as this vector. So if the vector moved around, which of course they can, then E1 and E2 would move around with them. Dogs. Hey! Oakley, Paisley, knock it off.